All right, let's get into rivers and streams. Okay, I'm going to start with this, one of my favorite videos. This is going to be in Alaska. Let's watch it. Okay, I don't really have any sound, which I apologize for, but it goes underneath the water. See what's happening here. Can you see all these pebbles that are rolling along the bottom? Like large sand grains and pebbles rolling along. Because the water has a lot of force, it's moving them along. And this is, look at that guy there, just kind of sliding along. The bigger ones that don't move as easy, but it slides along. I like that. It's getting pelted by the other rocks. So this can happen. A lot of times you find rocks, they may have traveled hundreds of miles like this, rolling, hitting other rocks, sand hitting it. You have a lot of abrasion. So the main thing I want you to get out of this about streams is that the sediment in streams are rounded from this process for abrasion. Man, I could watch this all day. Look at this. Captivating. Look at this. Right? But so a lot of rocks, a lot of material is moved by rivers and streams all day, every day. The faster the water, the more it can move, and the bigger particles it can move. A raging river can move rocks, that can move rocks at this big or bigger. So, all right, we'll stop that. And we're going to keep going here. What do we got? We got this. All right, pause and copy this down, please. Okay, so when I say streams, I really mean any sort of water moving in a channel. Streams, rivers, creeks, anything like that. And move sediments three ways. In solution is when minerals are dissolved in water, like halite. Like for instance, if you go to the ocean, it's salt water. Well, that's because the mineral halite is dissolved in that water. But we're not going to worry too much about that. In suspension is clay. Like a best thing would say, like muddy water. If you had a big bucket of muddy water and it was really muddy and cloudy and looked like thick chocolate milk, for instance, with mud, and you let it sit there for 3 days, that mud will settle out and the water's clear. That is what particles being in suspension is. They're small, super small pieces of rock or mineral that will settle to the bottom. That's in suspension. And then like saltation, so what we just saw, larger particles rolling, bouncing, skidding along the bottom. It's called bed load, and we'll kind of show a diagram of it there. Okay? So next up, please pause and copy this. So all of the material, rocks, pebbles, sand, etc., is moved by a stream. It's called the stream load. The stream load. That comes up sometimes. Stream discharge is definitely important. That's the amount of water flowing in a stream at any given time, right? Discharge. So if it rains really, really hard yesterday, and then you go down to a stream, the water will be really rushing in the stream much higher than usual, much more water, a much higher discharge at that point. And the graphs work this way. The more discharge, the more stream load, the more rocks and pebbles it moves. Kind of makes sense. Slope, if I do flatter slope to steeper slope, the steeper the slope, the more stream load, because the water goes faster. Okay, and you also have a bit of a slope like this, but the water goes faster, can move really big rocks. They often say, they say something like the water has an incredible force. They talk about you crossing a stream, and they say you should never cross a stream, like eventually if it's a raging stream, if it's like deeper than your knees, it can knock you over and take you downstream, and you could drown and die. So be careful of that, because it has such force, even just up to your knees. So that's just gives you a sense of how fast the stream could go, which is this too. Velocity, the fast, this is all kind of related. The higher velocity, low velocity or speed, lower speed, higher speed, more stream load. Okay, so this, hopefully you will need your reference table. This is page 6 of the reference table. Okay, what this is a chart that basically shows the speed of the water and then the size rocks that it can move, or sediment, sand or pebbles. We don't really use the word gravel. Okay, that's here, page 6 of the reference table. Hopefully you have it, okay? So, what do I have here? I have, wait a second, what did I do? Where's the colored one? Okay, there it is. Whew. There's the colored one. Holy cow. Nope, I want this one. What am I going to do? I'm going to do that. Here's the colored one. So what I did here, I went in and added these sweet colors based on the different sizes. We use this chart kind of a lot, and it's how we classify things. This is the size of it. You measure the diameter of the pebble this across, how big it is, in centimeters. So this is, let me go. I'm going to go like this. I'm going to go like this. So this is in centimeters, 0.01 centimeter, 1 centimeter, 10. So basically, the smallest ones is clay. That is the particles that make up muddy water. They're super, super fine. You can't even really see them without a microscope. And then a little bigger is silt. A little bigger is sand. Okay, I think you know what sand is. And then you go to pebbles. Above pebbles is a cobble. So a cobble is between 6.4 centimeters. So anything bigger than 6.4 centimeters. I have a ruler on my reference table. You probably don't. I wish that you did. We used to have them on there. 6.4 is about that big between my fingers. So anything bigger than that to 25.6 to about this big, that's called a cobble. Above this big, it's considered a boulder. Okay, so that's just, I did that. Now it's going to be stream velocity there. So what I'm going to ask you to do is pause this, use page 6 of the reference table, try to answer these questions as best as you can. Some of them ask for sizes, some of them ask for names of sediment. Do your best. If you get it wrong, I don't care. You'll fix it, don't worry. Good luck. Okay, I'm back. A particle with a diameter of 0.3 centimeters is classified as what? Let's go back. 0.3? Yeah, 0.3 centimeters. So I got to look here. Look here is really the best way between this. This scale over here hurts people's brains. I always tell kids to go over here. So 0.3, you got to... 0.3? Yeah, 0.3. 0.3, you got to look. Well, that's 0.2. 0.3 is going to be above it, between there. So it's going to be a pebble. So that first one should be... Can I write on this? I don't know if I can. Well, I think I can write on it. They don't have markers here, so I'll... that's a pebble. Oh, here we go. Pebble. Oh, that's pretty good. Pebble. Next up, what is the approximate minimum stream velocity? What does minimum mean? The least it can be. What's the slowest the water can go to move a particle that is a boulder, 25.6 centimeters. This year's 22, so 25.6 is about this big. What is it? How fast does the water need to go? So we got to go back to the chart. Where are we going to go? We're going to go here. 25.6. So this is how this works. How am I going to get this? Right? So I go 25.6 here. I go to this line, and then I follow it down like this. Right? And then I see that's 100, that's 500, I got to count. That's 200, and then the units here is crazy. Centimeters per second. Yes, I agree with you. I wish it was in miles per hour too. That's we measure stuff in miles per hour, but here it's centimeters per second. You don't think of speed in centimeters per second. I don't think of speed in centimeters per second. And I'm a science teacher nerd. I don't even think about it. But it's 200 centimeters per second. It just is. So 200, and it's very important to have the units on there. It is really important because 200 centimeters per second and 200 miles per hour, for instance, are very different. So next up, the velocity of a stream is decreasing. It means the velocity is slowing down. The speed is getting less, so the water is slowing down. Maybe it's going down a steep hill and it goes to a flat area, so the flat area is going to be going much slower. As the velocity approaches zero, so it goes to almost not moving at all, like in a lake, the water almost doesn't move, right? Which particles are most likely to remain in suspension, not be deposited? Well, so you have to apply a little bit of this and know in your head, it's going to be the smallest ones, right? The smallest ones are the ones that are going to stay in the water and take a long time to settle out. So the answer here would be clay. Now, kids often get that wrong. If you didn't really understand that, don't worry about it, but hopefully you understand it now. The velocity of a stream is 100 centimeters per second. What's the largest diameter particle that can be transported? So what I was really looking for here was the diameter in size, the largest diameter particle. So what did I say, 100 centimeters per second, right? 100 centimeters per second. So 100 centimeters per second, here I go 100 centimeters per second, and then I go up to this line here, and then I go over to there, and it's 2 centimeters. So it's a 2 centimeter pebble, about that big, can be transported. Now, if you wrote pebbles, I understand that. My question wasn't that clear. 2.0 centimeters is really the best answer, but you could have written pebbles, and then I'll take that on me. My bad. I didn't write the question clear enough. I apologize for that. What did I say? 2.0 centimeters, or pebbles, or pebbles. If you're not enjoying this, because all of them like this chart, I get it. We don't have a lot of reference table on this unit, so this is all we got. So we can handle it. What is the velocity necessary to carry the smallest pebble? Smallest pebble. Let's find the smallest pebble. Where's the smallest pebble? So I'm going to go like this. Let me go here. I'll go like this. And then I go here. Smallest pebble is here. So the smallest pebble is right here. So I'll go over to that. Let me go like this. I'll go over right to the line. The line, it tells me all my information. The line tells me the information about the speed of the water and the sediment it can move. And then I follow it down to here, and I get 10 centimeters per second. 10 centimeters per second. Units are super important. Put units on everything that has a unit. So hopefully that makes some sense for you. To you. Let's move on. Okay, so at the bottom of that page, please pause this and write this down. We're over on the right. Okay, what this shows is watershed, okay? And a watershed is all the land that drains into a river. So for instance, the blue here is the watershed for this particular stream right here. And the drainage divides are like the peak of the ridge, where water on this side, on this side of the drainage divide, it will go in this river. On this side, it goes over here, or this also too. So this is the whole area that will drain into that particular section of the stream. I'm going to show you some examples in this right here. Hopefully it makes more sense. I like this picture, shows it really well. So this is the drainage basin right here of this particular river. All of this land, when there's runoff and the water hits the ground and runs off, it's all going to end up in this particular stream. Water over here, if rain hits here, it goes into this stream and ends up off over there somewhere. Okay, so what do we got here? This here, I like this. This is green. This is the this is a watershed of the Mississippi River. Okay, this is about half of the U.S. Half of the U.S., when it rains, that water will somehow end up in the Mississippi River in the Gulf of Mexico. So there's a reason the Mississippi River gets so much discussion and such a big part of this country, is because it's just so much of this country will drain into the Mississippi River. Even other big rivers like the Missouri River, Ohio River. So that's cool. This, getting a little closer to home, the great state of New York, right? So here we go, New York City here, Long Island here, Adirondacks here, Buffalo, Rochester, Syracuse, Binghamton, Albany. So this, can you think of what drainage, what watershed, let's call it drainage basin, that's why I call it that. What watershed of what river this might be? Just think about it in your head. If you can get it, great. I'm going to tell you now. Hudson River. Okay, the Hudson River. All of this land drains into the Hudson River. And we do this because if let's say we go, oh, the Hudson is polluted here. It's like an oil spill. There's oil in the Hudson River. That's really bad for the people and the fish. We go, we have to figure out where this is coming from. If you want to figure out where it's coming from, look in the green. Don't look over here. If there was a big oil spill here, it would not end up in this river. It would end up in the Genesee River or something else, right? So that's kind of part of the idea here. Something else I want to point out is rivers. One of the key thing here, rivers erode. They have a lot of erosional force, so they're going fast and they're moving a lot of rocks along, and they erode V-shaped valleys. You'll see, or maybe you've seen it already, glaciers will erode a U-shaped valley. V-shaped valley, that's a really good picture of it there, because it's continually down cutting, and then you have landslides that come in and keeps bringing it downstream. So this is what happens. This is going to be many years. This is going to be thousands of years, right? So you have a river in the mountains, right? It's really steep, flowing fast, V-shaped valley, a lot of erosion. Rocks are falling in the river. It's taking it downstream like we saw earlier. It's bringing it hundreds of miles downstream. So as you continually erode rocks away from here, let's go forward. and this could be, I don't know, 20,000 years, thousands of years, it might look like this. And it looks almost so different. Like, where did the mountains go? Yeah, they got washed downstream or into the ocean, right? And then now this is eroding here and here. So this is called a floodplain. And then as time goes on, that even gets wider. And then you look at this and goes, oh, this is a nice, really slow flowing river. It's got a lot of curves called meanders in it. Great. You never would think there'd be mountains there. There would have been mountains there at one point, but there was. They've just been slowly, really slowly eroded away. So this is also goes with like landscape, how landscapes change. And what do I got here? Oh yeah, so this, I like this. This is a V-shaped, really shows the V-shaped valley here, right? You see this? Really V-shaped. You can see the water's really flowing fast, a lot of energy. You know, probably landslides down here into the river and it washes it away. This is in Wyoming. This is in Yellowstone National Park in Wyoming. So when I was there in 2015, I took this picture. Is it in it? I took this picture. Okay. Myself, that's me there with a beard. Don't have it anymore. But I saw this here. That's the river. And I go, I know this spot. Took this picture. Look at that kid. He's not enjoying it as much as I am. And then I said, this is the picture I've been using in class. Oh, come on. Oh, no. Wait. Hold on. Hold on. This is going to work. Let me do this. I said, this is the picture I'm using in class. And look, I'll put it over there. Put it right over there. Look, that's the picture. I had to mess up Mrs. G's face. Sorry about that. I don't know. That's the kind of stuff I like. I don't know. Let's pause and copy this, please. Okay, the stream bottom affects the speed of the water. The smoother it is, the faster it goes. Really, a lot of rocks and stuff is going to slow it down. Friction with the air above slows it down. And the velocity is greatest just below the surface. The diagram below is going to help us with that the best. Curve in a stream is called a meander. This is really important. Look at stars over here. The water moves fastest on the outside, so you have a lot of erosion there. It slows down on the inside, so that's where it's going to leave pebbles and sand behind on the inside. So let's look. Snickers. Everyone likes Snickers, right? I love Snickers. I don't eat them as much as I used to, watching my weight. But, so, whoa, that was a little blip there. So Snickers. So this would be called, if I'm looking at this Snickers bar, we'll call this a map view, looking down from the top. Okay? I have a reason here, not just because I love Snickers. And this is not in any way sponsored by the Snicker Corporation. Okay, so that's the map view of Snickers. Now, this, if you cut down, oh, look at that, man, nougat, nuts, caramel, oh my God. If you cut down, look at it from the side, that's called a cross-section, a cross-section. Now, we can cut through a Snicker and look at a cross-section. There are some other things that you can't cut through it and look at it, okay? So, they could do like a cross-section, they will draw cross-sections of the land or cross-section of your body. They don't do it by cutting someone in half. You can't do that. But cross-section, so oftentimes we have cross-sectional views. We're going to talk about cross-sections of streams. Now, you don't go to a stream and cut down into a river and move the land apart to see what it looks like from the side. You can't do that. So we have to sort of draw a picture of it. We'll get into that, right? So we'll get into that. So here we have a river. I said it's faster on the outside, so the water can go to the outside, slower on the inside. This is sort of the cross-section of the river the way they drew this. So you have erosion out here. Look, it's eroding the bank. And it's depositing here. So please pause and copy this. Okay, so look at this. A, and that's called A prime. And let's go A prime is how they do it, right? So outside of the curve is fastest. Because it's fastest, it's going to make it deeper, right? So towards the outside of the curve right there, the water goes fastest right there, and the shape of the bottom is like this. Okay? Where the river's straight, you don't really have that so much. B to B prime, so it goes this way. This is a more bowl shape. The water's fastest in the middle, down a little bit from the surface, right? And then C to C prime, this C is the outside, C prime is the inside. So it's shaped like this. You have deposition here, sand, pebbles piling up there, so it makes it shallower. Deeper out here as it erodes the outside bank. This is very important. Oftentimes on tests, you need to draw these. Draw what it looks like. Draw a cross-section from A to A prime. And they just give you a line. to draw it. So know that because that might be on a test or the Regents exam. Here, I like this picture and that it shows the different colors. So where the stream is straight, it's fastest there. On a curve, the maximum velocity, fastest speed is like right there, the darkest blue. Good picture. Good job, Pearson Education 2012. Oh yes, at the bottom of that page. Yeah, so due to the speed of the water, erosion outside, deposition on the inside. And yeah, so we have that. Okay, I see where we're going. Oh yeah, okay. Do I leave that in there? I did leave that in there, didn't I? Okay, right. So over time, where the river's pretty flat, it's going to get more and more curvy, and that's going to happen. So, so this is kind of cool that happens. Copy this if you have it. Pause it and copy it. Okay, I love this picture because what you have where the land is pretty flat, the water's not going super fast, so it's going kind of slow. So erosion on the outside, deposition on the inside. I think I may have missed a page here. Right, so what's going to happen here? Look, there's erosion here, erosion there, goes around erosion, whoa, erosion there. It's going to cut through at some point. And what you get is an oxbow lake, one of my favorite. You get left with something like this, oxbow lake. This river used to flow this way and back, and now it's changed and it flows straight through, which is crazy. So to show that rivers really change. These things change, they're not always the same. We got to think about that. You look at a river and go, it's been that way my whole life. Yeah, but over hundreds of years it does change. Okay, what is that where I had that? Okay, I'm just trying to think. Some of this, oh, the order got a little mixed up. Okay, here we go. Here we go. So here, but sometimes, unlike what I said, this can happen really fast, especially with storms. So in this case, this is 3 months. All this land was eroded away. Now this guy's garage over here is in danger of getting into this river. That's a problem. So ways to prevent. Pause and copy that now. Ways to prevent or reduce damage from stream erosion. Don't build in the floodplain. Don't build in right near a river where it's going to flood, because rivers flood. It's natural for rivers to flood. If you're built your house right in the banks of a river, it will flood at some point. Build levees. I won't talk about that. But armor the shoreline with walls or boulders. All of these things we try to tame nature, but they cause these other problems, and we've really driven ourselves crazy as people trying to control nature, and especially rivers, because there's rivers kind of most places. There are rivers around, and towns and civilizations built up around rivers because it has fertile soil, because of transportation, for fish, for drinking water. And then we try to control the river, and we just kind of continually lose. So that's just something to point out. So please pause and copy this now. So we're talking a little bit about deposition here, and the fast sediment, how fast sediments fall in water. The bigger the particle, the faster it settles in water, because there's a lot of resistance in water. Not so much in the air. Two things in the air will hit the ground at the same time. But the bigger particles settle faster, and that's what the graph would look like if size versus settling rate. Rate is the same as speed. Density, think of with higher density, metal versus plastic. And there's a video you'll watch, or maybe you've watched it already. But the denser it is, the faster it settles. Some minerals and rocks are denser than others, and they will settle to the bottom faster. And then shape. The flatter it is, the slower it settles. And this is a graph that I drew here that shows rounder settles at a faster rate, flatter settles slower in water. Pause and copy, please. Okay, stream sediments, rounded, the constant tumbling, the constant abrasion, sand hidden, it will be rounded, and they tend to be sorted as well when they go out into a lake or the ocean, tend to be sorted. And they're deposited in flat layers that are called beds. And these beds, you have beds of mud, beds of sand. It can be really, when they get compressed into rock, we call the beds to be sedimentary rock. I love this picture in that here we had, this is in New York State, this is in maybe Cayuga Lake, I think. Right, rivers coming in, bringing all this mud, and you can see the rocks and pebbles are probably right there, but the mud's getting carried out. This mud here, it may take weeks to settle to the bottom. Maybe this lake is a few hundred feet deep. So weeks to settle to the bottom, that mud's fine particles settling through water. So you can have Clay out here, silt, sand, pebbles over there. This too, this is in Argentina now. You see the muddy water, and you see as you go in here, it's getting carried out and it's going to settle to the bottom. This is a pretty sweet drawing that I did. It's a pretty sweet drawing. Pause and copy this, please. Right, hold on. Two types of sorting: vertical sorting, graded bedding. Vertical means as you go vertical, they're in order, larger to smaller. Okay, and then this is graded bedding, series of them there. In the real world, that's a pen. This shows larger, so smaller. This usually means like a landslide went into the ocean or into the water, maybe a lake or ocean or something. Pause and copy this, please. Right, so horizontal sorting is this. As horizontal is this way. Horizontal is flat. So this goes as the stream goes in. You have larger particles here. They'll be rolling along. Once they hit here, they'll just stop. The water's not moving anymore. Pebbles get pushed out a little more. Sand takes a little time to settle down. Silt, and as you go further out, is clay. This occurs because the speed of the water decreases when it empties into the ocean or lake. So, and then this area here is usually a delta. It will kind of build up, and there's other videos that will help you with that. This kind of shows it. This is from a Regents example, larger to smaller. And what am I going to do here? I thought, what happened to my last page? Come on, last page. I apologize for this. I apologize. What happened to my last page? I have it somewhere. I got a lot of slides here. Right, 1, 2, 3. This is the floodplain as time goes on. As floodplain formation, there's so much erosion here, erosion. It's a floodplain. And so when the river floods, you have heavy rains, that's the area that gets covered by water. That's where you don't want to live. If you live there, your house will be underwater. Which a lot of people live there. It's kind of bad. And is this next? What am I doing? Where's that other? I have adjusted this file a lot over the years, and I can't find it, and that's going to have to be okay. That's going to be okay. At the bottom of that page, it just shows Oxbow Lake Formation. It's just cool, something I really like. So I don't even have you write anything in there even, so. Thanks for watching, everybody. Hope you enjoyed learning about erosion. I'm Mr. G. Thank you.